Welcome to the TOPML talk by Edgar Dobriban. I'm happy to introduce Edgar, man of many talents here. He has joined Wharton when I was a PhD student there, and he has been working on various stuff, uh, before and since then. He has worked on several topics, too many to list here exhaustively, but he has worked on sketching, multiple testing, distributed learning, overparameterized models, conformal prediction, function spaces, everything. And he has recently gotten the NSF Career Award, and congratulations. And he has also gotten the NSF Simons Award, and he has been doing a lot of stuff on overparameterized models. And today he is going to tell us about an optimal test for calibration of predictive models. Take it away, Edgar.
Yeah, so thank you, Arun, for the generous introduction. I'd also like to thank the organizers for putting together a really wonderful workshop. I have learned a lot by listening to the talks, and it's a great honor to be here. And so my talk is related somehow to overparameterized models. It's not explicitly about interpolating overparameterized models, so I apologize if that's exactly what you're expecting, but I'll try to emphasize the connection. So anyway, this is a joint work with my colleague Ahmed Hassani from electrical engineering and our students Dongwon and Shimeng. So as we all know, we live in an age of machine learning being successful and becoming more and more successful in a variety of domains. And this is largely due to the success of big overparameterized models, especially deep neural nets, other things including data and computation power and so on. But really, it's the models that we managed to make successful. And you can hear about all kinds of successes in the news. AlphaFold, this algorithm from DeepMind, which predicts protein folding. Given an input sequence of a protein, it produces the three-dimensional output of the predicted structure of the protein. So it is it produces it by learning. It has achieved some pretty impressive looking results that you can see here from their paper. It predicts very well. And it has been chosen by the journal Science as the scientific breakthrough of 2021 among millions of scientific papers that have been published that year. So it's really it's outside of the community of machine learning. So it's really somehow impressive. Another example from natural language processing, GPT-3 from OpenAI. It's a language model. For instance, if you give it some input like a title and a subtitle of an article, it can be trained to produce a completion of that article. It writes the article. And this is an example from their paper that humans actually have had a lot of difficulty in telling apart from ordinary humans writing. So it looks like a human article. And at the same time, these successes come also with some growing concerns as well, including whether these models are safe, do they respect human ethical norms, are they energy efficient, sample efficient, and do they convey uncertainty accurately? And somehow these concerns to some extent are also due to overparameterization. For instance, things like energy and sample efficiency, well, bigger models in general are more computationally intensive to train. So, it's kind of a curses and blessings of overparameterization. And today I will talk about one aspect of this, namely uncertainty quantification. So what does that mean? For me, this talk, it will just mean that given an input X in a machine learning problem, the output Y may not be uniquely determined. So for instance, in GPT-3, I may be given a text prompt. Would I expect the output, the text, to be automatically uniquely completed? And the answer is in general no. Of course, given a title of an article, there might be multiple different articles that convey the same message. Another example that I let's say consider skin cancer classification, where given an image, we want to classify it into a number of different types of cancer. If the So this is another example where deep nets have been very successful. Given a very high quality image, maybe we can think it's unique, but given a lesser quality image, it might not be uniquely determined which type of cancer out of like hundreds of kind of small types there are it belongs to. So, and somehow the standard machine learning pipeline, especially in an overparameterized setting, does not provide a solution. So I'd like to contrast here sort of what we know from the classical, maybe statistical literature, where we may formulate a model and we may be able to have a consistent estimate of the parameters, which may also have some known asymptotic distributions. In this case, we can easily derive some predictive distribution, let's say the conditional distribution of y hat given x. And so we have a lot of tools to do this type of uncertainty quantification. But in the modern setting, it may not even make, so that a lot of that kind of goes out of the window, because we don't generally expect consistent parameter estimation in obvious forms, and there's very little about asymptotic distributions, like asymptotic normal distributions, for instance. So we have relatively more limited set of tools. There are still some tools, and I'll talk about it, but it's kind of, this problem is much more challenging in the modern overparameterized setting. So just to kind of give you a few two type of problems that one is interested in this area. One of them is that of forming prediction sets. So for instance, in a multi-class setting, given an input x, I want to form C of x is a subset of y. So normally in classification, I would output one label, but here C of x would output a subset of labels of y. And I want to ensure that when I sample a new pair xy independently from a C, then with probability at least 1 minus alpha, y belongs to the set predicted by C on x. So another problem which I will talk about here is that of calibration, which is slightly different, and it says I want to construct probability predictions that reflect the true empirical probabilities of the different classes. So suppose that I have let's consider a binary classification problem first. So y is 0 or 1, and suppose that I construct a mapping f of x that given an input x maps between 0 and 1, and it is the predicted probability according to my according to me that x belongs to class y. So then what I would hope is that if I actually output a predict probability, let's say 0.8, then the true class of y equals 1 should be 0.8. So this is what is called calibration, and it's I'll talk about it a little bit about the history, but it really dates back to ancient dates back to meteorology, where people were trying to predict the weather and the probability of rain, and given that I predict the probability of rain 0.8, it should rain 0.8 a fraction of the time. So there's been a lot of work on both of these problems, and as one partly because I think it's an important topic to know about. It's kind of a little bit outside of the standard machine learning curriculum. I've been developing a course at Penn that aims to kind of bring together a lot of the different topics in this area of uncertainty quantification for machine learning. So, and the materials are, a lot of the materials are publicly available on GitHub. So, okay, going back to calibration. So here we have, more precisely, we have this input x in RD. It could be an image or d-dimensional input, and we write the output as a one-hot encoded label. So 0, 1 to the k, but only one of them, only one non-zero. And so we will consider probabilistic classifiers, also known as probability predictors, that map the inputs into probability distributions over the k classes. So they don't just give you an output, but they give you an entire probability distribution over the classes. So I will use the summation delta of k minus 1 to be the simplex of the probability distributions over the classes 1 to k. And this classifier is called calibrated if for every class k between 1 to capital K, the probability that y belongs to the kth class, so y sub k is 1, given f of x, let's say I condition on f of x and they denote that value z, is actually equal to the kth coordinate of f of x. So this is just a multiclass version of what I said previously about the binary case. This is some sort of the most general notion of calibration. There are a bunch of other versions. This is the most general one. And just to give you an idea of how this looks in some deep networks, I also need to introduce a notion of top-1 calibration, different type of calibration, where given this multiclass classifier f of x, I only require that the top label prediction is calibrated. What does that mean? It means that I look at, let's say I predict the class whose basically probability prediction is the largest. If there's a probability that's 0.8, I choose that one as opposed to any of the other ones. I call that f plus of x, and y plus being the indicator that y is equal to the predicted class. K hat is the class that is actually being predicted, and I just, for simplicity, let's assume it's unique here. So for this f plus and y plus, this notion of calibration is exactly this equation. So it's just saying that the probability that y is equal to the correct, y is equal to the predicted class, given my confidence of the largest class, is equal to the confidence of the largest class. So this is actually, turns out, what is most frequently evaluated empirically. And there's a very influential paper from Kilian Weinberger and his group that somehow showed empirically, drew attention empirically to the fact that there's a big problem with modern deep networks. So that they can be extremely overconfident and miscalibrated. So here's a plot. So this is called a reliability diagram. So what it shows is it bins the confidence predictions, the f plus values from the previous slide, in some bins. And for every given bin, it plots the accuracy, meaning the probability that y is equal to the prediction per that bin. And if the network was calibrated, we should see somehow things close to the diagonal here. But in fact, what we see is, let's say for between 0.8 and 0.9 confidence, the accuracy is 0.5. So the neural net is way overconfident. And so this is also in contrast, again, contrast overparameterized with underparameterized. Previously, 15 years ago, people did lots of experiments with smaller neural nets, and they found that they are quite well calibrated. So it's a problem somehow that only comes to light, or really becomes very prominent with modern larger models. So, and this has drawn a lot of attention to the problem, but in fact there's also a larger historical thread here that I'd like to just highlight a little bit, that in fact there's been knowledge, there's been research in social sciences that argued and tried to establish and found that somehow humans can also be quite overconfident. So I just to kind of very briefly go over some of the context here about the history of calibration, and some of these we will use later. So more than 100 years ago in meteorology, the meteorologist Cook, who was working in Australia, he suggested to express forecasts for weather as probabilities, and then he compared those forecasts with the realized frequencies of events, and found some pretty good agreement in some of his data sets. Then sometime later, Breer suggested to evaluate forecasts more quantitatively via some sort of a scoring rule. It's a kind of a loss function for probability predictions. So looking here, let's say P is the prediction of for some event between 0 and 1, it's a binary case. and A is the event, and I of A is the indicator of that A happens. So this is sort of a loss function, similar to the usual loss functions for that we use in statistics or machine learning, except that this quantity is now random, so it's a loss function for prediction. So, and this is now become known under the name of Brier score, and it's been widely generalized to other proper scoring rules. Later, statisticians, including distinguished statistician David Cox, proposed a formal test of calibration. Basically, he introduced the model called logistic regression in statistics, and he suggested to use the score test for testing logistic regression to test the calibration, and we'll describe this in more detail later. Another test was proposed by Robert Miller, another meteorologist, who suggested simply to use a chi-square test, which is another standard test in goodness of fit testing, to test the calibration of not just one sequence of binary predictions, but multiple sequences. Suppose you have multiple locations in time, multiple locations, or multiple kind of time windows, and you want to test calibration separately. So that's what that's what he studied. There's been a lot of work later, as I mentioned, in psychology and social science, including the well-known work on prospect theory by Tversky and Kahneman, that kind of also is in this line, showing that humans are overconfident. Also a lot of work in statistics and decision theory from Bayesian perspectives and recalibration. This attracted attention in other communities, including medical statistics and business analytics. And nowadays there's interest in the machine learning community. But anyway, I think this is sort of a rough historical outline, and we will use some of the ideas proposed by these people in our work. Okay, so going back to the formal setup, the workflow for achieving something like calibration would be to first get this forecaster or classifier, let's say train a neural net, and we could train for just accuracy, just as usual, or try to add some loss function that captures calibration. And then we would go and check whether it's sufficiently well calibrated, meaning sufficiently the probabilities that it predicts sufficiently well fit. This will be the problem that I will talk about today. The other aspect of the training is, a different topic. This is sort of an organic cycle somehow, that if we detect that the F classifier is not calibrated, then we would go back and somehow retrain. So I will focus on the testing part. Okay, so let's just again, to form the context, see what are the sort of well-known tests for calibration. So for this one, what we need is let's look at the binary events, BI. These are Bernoulli random variables with some success probabilities QI. And the most general setting is that we would want to test that QIs are equal to some given and fixed probability predictions PI. So PI is the prediction that I give for, let's say, rain happening tomorrow, or the prediction that the neural net gives for this class being in this image belonging to a certain class. And then we want to test that those are reasonable. So David Cox suggested, let's write down this logistic regression model of the logit of QI on the logit of PI with these simple intercept and slope parameters, and let's test the null hypothesis that beta 0 is 0 as well as beta 1 equals 1, so PI equals to QI, then using the score test, which is just the gradient of the log likelihood. It amounts basically to testing the gradient of the log likelihood. So the problem with this, it's a very nice, very useful idea. It's very popular in especially medical statistics. But the problem is that it assumes a very restrictive parametric model. So, and modern methods, we expect them to be more non-parametric, and then those types of calibration, miscalibration, may not be detectable using this. So here's just a picture that shows how this model looks like. So here is a plot of the predicted risk against the observed success probability. Or observe the proportion. So what we can see here is that this is the null hypothesis, the straight kind of diagonal, and this model corresponds to just varying beta 0 and beta 1, just traces out some sort of parametric curves. And certainly the example that we saw at the beginning with the neural net may not necessarily fit this this pattern. So what that means is somehow, if we're restricting ourselves to these parametric models, we may not be able to detect easily certain types of miscalibration. So the other well-known approach in the area is that proposed by Miller, who suggested to somehow group in some suitable way these success probabilities and then use the standard chi-square test, goodness of fit test, for the per group average predicted vector of probabilities. So I average the PI in every group and then check the average probability against that average. So, and it's well known that it has a problem, which is how to define this grouping. And so it's basically there is no good solution in the literature for this. So those are the kind of existing methods and their limitations. And in addition, when you start thinking about the problem, there's a few other kind of key questions that one can identify, including, should we use the score test or should we use the chi-square test? Which test statistics should we use? And what type of optimality properties do they have? So under what conditions can we say that this is as good as possible, for instance? So our work proposes method called TCal, which is a test of the calibration of predictive models, multi-class classifiers. And so I'll try to convince you how it answers some of these questions. And in addition, I'll try to show some experiments showing that it can be readily applied to test, if any big, deep neural net is calibrated or not. So just intuitively, what we will do for the question of detecting general forms of miscalibration, we will simply follow the suggestion from Miller to use a non-parametric testing model and a chi-square type test. So we just, that's a well-established, it's a well-established idea. We will follow that. But for the problem of choosing the groups, which is a challenging problem, turns out we have been able to come up with a binning scheme that is adaptive to the sort of true smoothness level of certain things which I'll define in a second, basically this kind of calibration curve. And we borrow some ideas from non-parametric hypothesis testing where such things have been used in the past. And for the problem of choosing the test statistic and optimality, this is one of our main innovations that we figured out how to construct a very carefully debiased plugin estimator of the calibration error, which I'll explain in a second. And then further, we've been able to show, again, borrowing from non-parametric hypothesis testing, we've been able to show a concept of minimax optimality when the calibration curves are sort of Hölder smooth. So that's a list of our contributions. And this is how our test effectively works. Given some features like images or labels, we assume that we have a pre-trained probability classifier, which gives us probability scores, predicted probability scores. And then what we do is we construct these binnings we bin these f values at multiple different scales. Here I only show it for in the one-dimensional case, the binary case, but in general we need to somehow bin the simplex of probability scores. And we compute some test statistic, which I'll explain in a second. It's some sort of new test statistic that's a good estimator of the true calibration error, and then we do a test at every different sort of smoothness level. If at least one of them is rejected, here you can see somehow that at this level, the deviations are relatively larger than at this level or this level. So if at least at one level is rejected, the hypothesis of calibration, then we say, okay, it's not calibrated. On the other hand, if it's accepted at all different levels, then we also accept or do not reject the null hypothesis of calibration. All right, so that's just the overview, and now I will go into the details a bit more formally. So this was the definition that we used for multi-class classifier being calibrated. The conditional probability of yi equals to 1 given f(x) equals z is zi. So I can equivalently write it as this regression equation. The average value of y, this sort of one-hot vector conditional on f(x) equals z is equal to z. So it's a sort of a equation that has to hold for all z if that's in the range of f. I just say here for all z in the simplex for simplicity. And so some terminology that we see here is important. Is this curve is called the regression function. We call it the regression function, and especially in the binary case, other works have called it the calibration curve. So I will just use this notation reg f. It's just a regression function. And so the residual function or miscalibration curve is just this regression function minus z, which basically has to be 0. So classifier is calibrated if and only if this residual function is 0 with respect to the almost surely with respect to the law of the probability distribution of f of x. And so okay, so this is 0. So somehow we want to measure miscalibration about how large this function is. And exactly that is sort of standard definition of the LP expected calibration error is just the LP norm of this residual function. So this is how we measure the amount of miscalibration in an average sense. Okay, and so to be formal about hypothesis testing, we need to define the null hypothesis and the alternative hypothesis. So we will consider distributions over the predicted probability scores and the outcomes labels, which we will just denote z. And we will assume that the map that goes from the probability score z to every given coordinate of this sort of miscalibration curve is Hölder continuous with a Hölder exponent s. So this is the thing that comes in the f of x minus f of y is equal to x minus y to the power s. And this is just the sort of analog of the Lipschitz constant Hölder continuous for every k. This is a sort of smoothness assumption, and we saw there were talks earlier about what kind of assumptions we need to make. Talk by Francis earlier in the morning. Turns out, indeed, even here we'll have a result later showing that we need at least something more than continuity, because without continuity it's impossible to solve this problem. But I'll get to that in a second. So so with this, we will set a null hypothesis of calibration against an alternative of at least an epsilon calibration error. So the true distribution of the data belongs to P0. P0 is when the residual function is 0 almost surely, so the LPEC is 0, and the classifier f is calibrated. And the alternative hypothesis is that the probability distribution P belongs to this this set, which is such that it satisfies this Hölder smoothness condition, and more or less, and moreover, the LPEC, the LP norm of the residual function, is at least epsilon. So we're testing this equals to 0, LPEC equals 0 against LPEC greater than epsilon with some smoothness condition here. So there's an intuitive idea of how to solve this problem, which is essentially correct, but is just numerically suboptimal. So the idea is that if a classifier is calibrated, then by definition, the probability predictions of the labels match the true class probabilities. So we can just say given the existing features, I can randomly draw labels according to the probability predicted by my classifier F. And if it is calibrated, then they should follow the same distribution as the true distribution, right? So then I can just split the sample into two halves and do this on one half, and then use any classical two-sample test, which is a very standard problem in statistics, testing that two distributions are the same. I can just use any of those methods to check if the two samples are the same distribution, and implicitly I test calibration. So it turns out that this is actually is correct, and it even gives the optimal rate somehow, which I'll talk about. It's correct, but we have not been able to make it work numerically well. So here is a plot of some simulation where we increase the signal strength, the L2EC, and here we show the type 2 error, which is just the probability of falsely not detecting that there is a miscalibration. So the smaller the better. And here's a method that's due to here's a method that comes from this sample splitting, and here's our method, which I'll explain in a second. So you see it's much better. So our method is somehow much better. We haven't been able to make sample splitting work, but the idea is correct. So let me now actually introduce our TCal method. And so, okay, so the starting point is the form of the L2EC, which is this averaged L2 norm of the difference between the predicted probabilities and the it's the observed probabilities and the predicted probabilities. So intuitively, we want to define some sort of a plugin estimator of this quantity. And so let's say we start with a partition of the simplex, and let's say that the partition is indexed by some index m, which I'll say how to choose, and it has m to the k-1 bins. Of course, the simplex is k-1 dimensional, so it's kind of this is the natural scaling. And let I sub I be the data points. Let's say n is the sample size, and I sub I is the data points that fall into the ith bin. And so a natural plugin estimator would be just to approximate for every given bin this by the observed labels yj, and this by the observed features or probability predictions zj. And it leads to this type of basically plugin estimator. So that's a very natural idea, and it goes in the right direction, but it turns out that it has too high of a bias. So here there's a simulation where it's just a binary case, and the distribution of z is uniform, and the distribution of the alternative is this uniform times calibration curve is given here. So the calibration curve looks like it's over, it's under confident. Let me see here. So for small values of f of x, the y given f of x is the predicted probability of y given f of x is let's see how this works. So I believe that my true success probability is 0.3, but my actual success probability is 0.2. So it's underconfident here and it's overconfident here. And this may look like a little bit an artificial example, but again, in the era of overparameterization, if we can have very rich model classes, then conceivably we can get such behaviors that some function that we fit to the data or we interpolate some data with, it can wiggle a lot. And in fact, if you train neural nets in small dimension and you make them very complex, they can easily have this type of oscillating behavior. So the problem here is that this is miscalibrated, but the test statistic that we discussed in the previous slide is biased in the sense that it does not get larger. It should get larger because there is more calibration error. So here you see the distribution, and here you see in fact the mean under the null hypothesis of calibration. So it's right here in blue, and under the alternative of miscalibration, it should go up because the calibration error is large, but in fact it goes down. So and this is just not just a kind of finite sample effect, or we can theoretically prove that this is the case. So basically, this test statistic is biased for this type of highly oscillatory, some of these highly oscillatory calibration curves. However, it's a good starting point, and after some thinking, we came up with the idea that we might be able to debias it somehow. And the intuition is that it's biased because it's estimating two things at the same time. It's estimating both the conditional expectation of y given z over the bins, and the conditional expectation of just z over over the bin using the same sample. And we know that we haven't been able to get it to work with sample splitting. I mean, it does not work numerically well. So what in the end we came up with is this correction, which takes the original sort of plugin estimator and subtracts from it a variance term, which somehow this is somehow the main contributor to the bias. Turns out these are some sort of variance terms for every individual quantity here, and then even though this is still not exactly unbiased for a general L2 EC, it reduces the bias significantly, and we can show that it leads to an optimal test statistic. So that's what the theoretical result that I'm going to show next is. So we use this as a test statistic, and then there's a little difference of how to set the cutoff. Basically, if this test statistic is large enough, then we reject calibration. We reject the null hypothesis of calibration. How large? It's a little subtle, but if there are a lot of data points, if n is larger than the number of bins, then we can use a slightly different threshold. So I won't won't detail that. And in practice, we always use some sort of resampling or bootstrapping to set the critical values, maybe to choose this threshold. But the test statistic, of course, we still need to come up with. We can't do, that bootstrapping doesn't tell us what to bootstrap. Okay, so our main theoretical result, first one is that if we choose the number of bins appropriately in this particular form, n is the sample size, and S here is the known smoothness. So we assume here for the first result that the smoothness parameter is known and K is the number of classes. Then with the test statistic on the previous slide, our method, which we call TCal. So the TCal method controls the type 1 error, the false detection rate, and for every probability distribution for which the probabilistic classifier is calibrated so P is in the null, then the probability of falsely claiming miscalibration is at most alpha. So that's one side of the result, and the other side is that we also have a true detection rate control, meaning that the true positive rate is at least 1 minus beta for every P in the alternative hypothesis when the probability distribution is miscalibrated, and the miscalibration rate epsilon has to be at least of an order that's given here, n to the minus 2s divided by 4s plus k minus 1. So I'd like to make a comment again. If you remember from Francis Bach's talk, he was talking about the smoothness sort of as an inductive bias. And here what we see is that the correct, so the dimension is k minus 1 because it's a k minus 1 dimensional simplex. And this is exactly that expression that he also showed, and it's a kind of standard thing in non-parametric statistics. But basically here what we are saying is that with some smoothness, we know how to get the false detection and true detection rate control. And we will also show some, also state some lower bounds, but combined with that, it shows that our methods are minimax optimal over Hilder-Smooth calibration curves. But there is also the problem of the adaptivity to the unknown smoothness. And there again, we borrow a standard idea from hypothesis, from non-parametric hypothesis testing, that we do the test at multiple different scales. So we consider basically binnings with an M. Remember the M parameter in our binning at basically on our dyadic grid, 2 to the little b from 1 to capital B, and capital B is chosen as such so that 2 to the b is about about n, roughly speaking. And then we also need to divide the critical value, meaning the significance level at every given test, by big B. So this is we test every one of them, and the maximum here means that if at least one of them rejects, then we reject. So this leads to our sort of final adaptive version of the method. And for this one, we have the same false detection rate control without knowing the smoothness. And without knowing the smoothness, we have a true detection rate control result when epsilon, the level of miscalibration, is above the level n divided by square root log n to the same power. So again, just in case you remember from Francis' talk, he was talking about the logarithmic cost of adaptation to unknown smoothness. This is the logarithmic cost here. Maybe in 1D we know that it's not optimal, because in 1D it's known that it's only a log n. Actually, there's results from Spokojny from a number of years ago that say that it's only a log n that's needed. We don't know in general whether it can be improved or for other higher dimensions. Okay, so let me show you some experiments to sort of convince you that this can actually run on modern settings. So we compare our TCal method with some classical calibration tests that I already introduced, the Cox logistics score test, and also a sort of very popular approach, which is just to use the plugin version of the L1ECE, for which there is no sort of theoretical known way to debias it at the moment. And we look at a challenging setting, but again, this, if we have a complicated neural net, we can imagine that it's oscillates a lot. So maybe a calibration curve that looks like this one is still reasonable. And our first experimental result here shows here again, this shows as a function of signal strength, the L2ECE, the type 2 error, which is the probability of not detecting miscalibration. The smaller is better. So here we see in solid line our TCal method with several different sample sizes, 2,000, 5,000, 10,000, and it gets better with increasing sample size. For the other two methods, the L1EC and the logistic, we only do the experiment for 10,000 because it already, even for 10,000, you can see here the results for logistic, it doesn't seem to have a lot of power. Similarly, for the L1EC based test, it doesn't, it's much worse than TCal. So here our method performs better. And we did some more ablation studies to try to understand what are the reasons. So our test is different from other tests, including that it uses an L2EC as opposed to L1. It uses a debiasing, and it also uses the number of bins, which is chosen adaptively according to automatically adapting to the smoothness. So what you can, so we kind of did an ablation study on that, and what we concluded here is that the debiased L2, which is TCal, is still the best, but the biggest effect seems to be choosing the optimal number of bins somehow automatically. So you can see here, this is the result for TCal in solid, and then biased L2 without debiasing is slightly worse, and the biased L1 with an optimal number of bins is much better than it was on the previous slide, but it's still slightly worse. So to conclude, the number of optimal sort of automatically adapting to the optimal number of bins, is quite significant here. Okay, and we can also run this on a number of deep neural nets. We just look at standard data sets and standard models, CFAR 10, 100, ImageNet, and there's a lot of work on training. So post hoc calibration, which is first I train the neural net, and then I use a separate calibration data set to recalibrate it. But the evaluation in this line of work is not always very rigorous. So we don't actually know, even if the method decreases empirically the calibration error by some small amount, it's not rigorous whether it actually decreased it enough. There's a kind of limited kind of level of rigor in the experimental evaluations in this area. So our method somehow can be used to test some of these methods more rigorously. So on CFAR 10, we look at, let's say, ResNet 50, and without any calibration, it gives an this is just standard L1 EC to 2.something%, and we reject the hypothesis that it's calibrated. But even with these improvements, which are very popular methods, flat scaling, isotonic regression, and so on, histogram binning, scaling binning, even if they improve actually the L1 EC, they're still, or at least these numbers go down, right? We still don't know if, we still don't believe, based on our method, that the model is really calibrated. So we still reject the null hypothesis of calibration. And so somehow the results align with the magnitude of the EC, but our test statistic is different, so it's not always the same. So for instance, here in this CFAR 100, if we look at the ResNet 56, we can see that, for instance, this flat scaling is accepted with a 1.84% L1EC, but the scaling binning has a smaller L1EC and it's still rejected. So it's not, it's not the same. Our test statistic is not the same as L1EC. Okay, and visually the results sort of make sense, at least in some of the cases. Here's how an example looks that is rejected. It's one example that's accepted. And sort of for this one, visually, maybe we wouldn't know what to say, right? But our method, which is a rigorous hypothesis test, concludes something. And it turns out it concludes acceptance, meaning that there is not enough evidence to say that based on this data, that the model is miscalibrated. So, our model, our method is most useful in this intermediate regime, because these ones are pretty obvious, but this intermediate regime is where we can have the most benefits. Okay, on ImageNet, it also, we can run it, and maybe in the last 2-3 minutes, just to give you a sense of our optimality results and lower bounds. So in general, just like in the no free lunch theorems that Francis mentioned, we cannot expect to be able to always be able to detect miscalibration if the calibration curve can oscillate with arbitrary high frequency. It should be essentially impossible. So this result kind of codifies that. So here what we look at is a test psi that rejects when it's calibrated. So this is the probability that psi is 0, meaning that we don't reject. And we look at the worst case worst case of this probability of not detecting miscalibration over probability distributions where the calibration curve is only continuous, it's not necessarily smooth, and we want to find the best test. So it turns out that this result shows, for some value epsilon 0.1, it could be anything. It shows that this quantity, this minimax type 2 error, minimax risk, is as big as it could be, 1 minus alpha. So even if we don't do anything, if you just randomly flip a coin, then we would get 1 minus alpha. So this is as bad as it could be. So this problem is impossible. And with so that motivates us to look at some sort of smoothness. We could look at other types of smoothness, like Bessel spaces or something. We just looked at further smoothness, and we have the analogous definition of the type 2 error here, but only over the usual sort of Hilder-Smooth class. We have the so-called detection rate, which is the smallest epsilon prime here needed to make this type 2 minimax type 2 error go below beta. And so our result says that this type 2 that this detection rate is exactly of the same order as the upper bound. And this is the result that you would expect in general from the literature on non-parametric hypothesis testing. But because we are constrained to the simplex, and we have a different observation model, we actually need to do quite a lot of new work to show this. So we expect, the result itself is not, wouldn't say it's surprising, too surprising at least, but the analysis is still novel. Okay, it shows that our method is minimax optimal, and it says, small data sets and complex models, overparameterized models lead to a lot of challenges because the rate becomes slower and slower. You see, if the smoothness is small, meaning we have a richer class, we only impose small smoothness, then this rate gets slower. So that's some kind of conclusion. So overall, to conclude, recently I've been interested in uncertainty quantification, which is important for machine learning, and even more important, I think, in the world of overparameterized models. Calibration is one of the key problems, so compared to what people do, here we are saying that you should pay attention to statistical significance when you try to claim calibration or miscalibration, and specifically that some popular things, fixed binning, for instance, are somehow suboptimal in some cases. And to address these issues, we propose the TCAL, which is a sort of test for calibration, and it's available publicly. All right, so thank you very much.
Great talk, Edgar. Great talk. Thank you very much. I guess you put in questions if there are any. Maybe I can start. And so, do you need to know the smoothness of the reg function in order to implement this? The S.
Right, it's a good question. In this version, which is the adaptive version, we do not need to know it because we look at the multiple scales, right? But and we test the null hypothesis at each of the different scales, and then if at least one of them is rejected. But also, you see that there is a trade-off in the sense that the signal strength that we can detect is somehow larger than without looking at this adaptivity. So we don't need to know it, but also our result is, it says that you need a larger signal strength. And yeah, again, as I mentioned, we don't know if this is optimal in general. We only have the optimality for the known S case. Yeah.
And so how would one go up, because you mentioned specifically that this can be applied readily for deep neural networks or so on, how would one go about like verifying if the reg function for a particular classifier that we output has some kind of a Holder smoothness?
So that's a very good question. And in fact, what I think might be better there, it would be to try to look at what type of function spaces can neural nets approximate. So look at, I know that there's results on this, and even some of the organizers of the workshop.
But neural networks approximate the L2 space, right? They're dense in L2.
Well, yeah, but like sort of fixed, if you like somehow fixed width or like limited width or depth, certain like limited classes, or if you put L2 norm constraints on the weights, they would approximate. They tend to limit some type of function spaces, and I know like Gita Kriniok and Ingrid Dobeschis and many other people have worked on what type of function spaces they approximate sort of more naturally. And I think it might be good to draw inspiration from there to see how to detect miscalibration for those type of spaces. But so that's a very interesting question, but it might be also very challenging. But anyway, it's a very
I'm sorry, I'll ask one more question. Anybody else wants to jump in, they can please ask the question. If not, I'm going to ask one more. So I understand what you said about the neural networks with a fixed width and a fixed depth to try to see what kind of function space they approximate. But I worry that if you are allowing for arbitrary dimension of the data, don't you expect some more care in the analysis to ensure that even if the dimension changes or grows or goes faster with respect to even width and the depth too, even if I like do a bigger depth or a larger width, would you like, I mean, you can still say that, a function that has a holder continuity constant blowing up is still in the holder class, but it's blowing up too quick or so on. So you are asymptotic. The asymptotic that your results are asymptotic, right? You're not controlling the type 1 error finite sample.
It is finite sample, but it is also, you see, the dimension enters here. So, and this is, by the way, so what enters here turns out is the dimension of the number of classes. So it's just the number of classes, yeah. Right? Yeah. So somehow the reason for that is that
in the definition of the holder continuity.
Yeah, exactly. If I go here to the basically this is a hypothesis test about this object.
Right.
The calibration curve regression. So it's every value of y given fx equals z. So z is a probability score over all classes. So somehow it's inherently k-dimensional. K is the number of classes, right? It's s yeah. So it turns out that this is exactly what controls this. So it's both a kind of good and a bad thing. It's a good thing because the dimension of the original data doesn't enter there, but it's also like a limitation because what's the connection between the structure of the function f that the neural net computes and the structure of this function? So I don't know how to map them directly one onto each other. It's not so easy to directly use the sort of approximation theoretic results for neural nets. Yeah, but I think it's what you're saying is a very good, it's a very good kind of question. Maybe some future work. Yeah.
If there are any questions, please go ahead. Great talk, Edgar. Great talk.
Great. Thank you very much.
Yeah. If there are any questions, I guess you can reach to Edgar directly. I hope you have in mind.